Okay, so yeah, one of the big things that we do is real-time systems in Java. So we're interested in having some things specified in the OSGi forum to help support that. So why do we care? Well, the Internet of Things is exploding, and there's a lot of devices out there, and a lot of these devices have real-time aspects to their behavior. So, we imply convergence of miniaturization, networks, data analytics, et cetera, and you can't do everything in the cloud. And as soon as you have some kind of wireless networks involved, real-time is off. People talk about real-time data collection, but that doesn't exist. We have live data connection, and we want to make that distinction because we have, when we talk about real time, we talk about determinism, and that's not what you can get with such a network. So in a real-time system, you always have some control part, some sensor part, some feedback, and that closed loop, I think, as you found yourselves, has to be well controlled. And if you can't control it well, then you can't guarantee any kind of delays. And you want to separate that from the network because there's no way to qualify the network in a real-time sort of way. Like I said, the only thing you can get is really live data. So why OSGi? Well, a lot of these systems, you'd like to be able to add behavior as you go along, and not just build some fixed box that's real time, put it down, and never change it. And there's some use cases where you want to mix so real time critical things with things that are less critical, like talking to your network and sending data, live data streams up to the cloud. So OSGi gives us this way of configuring things nicely where you can actually change the behavior of things on the fly and still have it work. But of course, then you need to worry about robustness of your system. So, when we talk about real time, we say real time is not real fast. I mean, some people think if you make it fast enough, it's real time, right? No, that's not true. Yeah, you can be fast enough most of the time, but if you miss it sometimes and you're trying to do a control application, imagine actually doing autonomous driving where you have to ask the cloud what to do next. If you don't know what to do next in a bound amount of time, you're going to have accidents, period. And even data collection, if you really want to make sure that you get all your data, even if your cloud connection is not real time, but you want to make sure you don't miss anything, at least that part of the system has to be real time capable. Otherwise, you can miss important data. So, basically, we talk about deadlines. In what period of time must a response come or something be recognized? And if you miss that deadline, if it's a hard real-time system, you can have catastrophic failure. Now, there's some systems that they call soft real-time, where you can miss the deadline sometimes. I mean, if you're doing a video stream, if it's sometimes you drop a frame, okay. If you do it too often, that's a quality of service thing, and that's not good either. So you have to set up these systems to be able to do this, which means that the parts of the system that have short deadlines also have to have a higher priority. And when I talk about priority, I don't mean Java priority. Java priority is meaningless actually. There's no specification for it anywhere. It wasn't until relatively recently that OpenJDK started to use niceness for Java priority. Before then, it didn't do anything. And even then, that's just a relative fairness quality. It's not a real-time quality. So if you wrote, a Java 1 priority thread, you'd expect that it would make progress, even though there's a high priority thread that's running all the time. And that's not something you can't do in a real-time system. So we talk about a utility function. That's, this is starting from event 0. Actually, you can look at before 0 as well, where the utility, climbs to that point. And after some time, the utility of the information goes away. So when you write a real-time system, you talk about a deadline, which has to be on top of that utility curve. So you want to guarantee that you have a response in that time. Otherwise, you can't guarantee that the system will do what you need to do reliably. So in conventional Java, we have some problems with actually doing this. So one is the garbage collector. The way the garbage collector in OpenGDK or even Growl or these other systems works is there's a thread there that's doing garbage collection work, and sometimes it has to stop the rest of the threads, particularly if you're moving objects around in the heap or other things. So that means most of the time it's really fast, and all of a sudden, oh, not. So people do all kinds of funny things to try to get around that, and the garbage collectors get a bit better, but there's always situations where the garbage collector will stop everything in the system for an indeterminate amount of time. So JIT compiler is another inhibitor to real-time response because, if I interpreted code, it may be slow, but I know how long it takes. If I compile code with a ahead of time compiler, it's faster, and I also know how long it takes. If I have a JIT, all my bets are off because sometimes it takes longer than interpreting the code. And I don't know how much longer because that depends on what's going on in the system. Then there's the issue of scheduling, which I already touched on. If you need a real-time system, you also need real-time scheduling, which is priority preemptive. That means if there's a high priority task running, the lower priority task cannot run on that same core. Because there's no mechanism to have the high priority tasks be interrupted in a standard scheduling regime. So that means that when people design real-time systems, the high priority tasks need to have very well-bounded time so there's time left over for other things to run. And if that doesn't happen, then the system can lock up. I think we've had some developers in our office that locked up our OSGi system because they didn't pay attention to this sort of thing. And that's why there's things that you need in the standard to deal with that. So, what do you need for real time? Well, you need priority and affinity control. So you need to be able to talk about real-time priorities, not just Java priorities. Java priorities run below the real-time priorities. If you map them even if you map them in Linux, there's a real-time priority zone that's above the standard fair scheduler. The RTSJ also says that you should try to use fair scheduling for 1 to 10, which is sometimes challenging on a real-time operating system, but that's another subject. Of course, you need memory isolation is very good. Java gives you this. This is one thing why I hate JNI, because you can blow holes into your virtual machine. If I stay in Java, I can guarantee memory safety. People talk about memory leaks in Java. Well, there actually aren't any. There's just memory hoarding. I can hold on to an object too long, but I always have a reference to it. In C or other languages, you can lose a reference and it's just gone forever. With Java, at least I can use tools to find out who's hoarding stuff and do something about it. So that's actually a safety consideration. Code isolation, OSGi does a pretty good job of this. It gives you some additional facilities. But you also need resource enforcement, and that goes back to the scheduling problem. If I write a high priority task and it does something wrong, it's going to hang up the system. So how many people have seen a bundle hang their whole system? Yeah? Yeah. And that's without real time. It gets worse with real time. So you need some capability to limit CPU and memory use. Otherwise, all bets are off. And of course, you need admission and degradation control as well. Some way of dealing with, okay, I want to start a new service. Do I have the resources to do that? How do I manage that? And with real-time Java, we have a lot of the things that we need. We have well-defined scheduling. So if you have a priority that's above 10, it's clearly a real-time priority. In the new spec, you can differentiate between FIFO scheduling and round-robin scheduling. And the big difference is in a round-robin scheduling, your task is descheduled at some point. So if you have two tasks running at the same priority, they will switch between them. But in FIFO scheduling, that won't happen. The first thread will run until it blocks. Right? Then you have a multi-threaded, fully preemptible garbage collector. This is important. What we do is a little bit of garbage collection work at allocation time so that one knows precisely where in the code the penalty is paid for allocating an object. That makes the allocation a bit slower, but at least you can say something about how long it takes, which you can't in a normal Java system. Of course, you want to link only the code you actually need. JLink is a one way of doing this, but it's relatively say coarse-grained. There's applications where if you're trying to do something really small, so you want to have something come up quickly and go away, that you want to do a much finer implementation, or even if you have some control that has to run on a fairly small device, you want some way to do that. Ahead of time compilation is very important, again, for worst case execution time. And finally, you need support for things other than Linux, because Linux is not the only thing out there. So the real-time specification has, in the new version, we've divided up a bit, and the reason why we divided up is that there are facilities that not everybody would like to have or need. And of course, some of the facilities have an impact on the rest of the system. Particularly the alternative memory, scope memory implementations does have some impact on overall performance. But the core has well-defined scheduling, basically fair scheduling for 1 to 10 and real-time scheduling over it, real-time threads, and event handling. Event handling is a very nice way of talking about real-time systems, because instead of writing a loop and having an explicit block in your loop, you can say, look, this is some computation that should happen every 10 milliseconds. And I can just hang it on an event that fires every 10 milliseconds, and I don't have to worry about it anymore. That makes the code writing easier. It makes it easier to write high-priority tasks that are well-behaved, because I have this nice limited computation where I can do better estimation of how much time it takes. Then I have priority inversion avoidance. In Java, if you go into a monitor, all bets are off, right? That means if I desynchronize on something, I don't know who gets to run when. In the RTSJ, there's rules about which thread gets to enter the monitor first to ensure that there's no priority inversion. Because you can have a situation where high priority tasks blocks on a monitor that's being used by a low priority task, and then some medium task comes in and blocks the low priority task. That means you lose your deadline. But with priority inheritance, as soon as the high priority task requests that monitor, the low priority task is boosted to the high priority, so I can finish that synchronization block and then drop back down again. And this way, we can ensure that the system works even under real-time constraints. And then we have monitoring and control. You can ask if deadlines have been met, get some notification, actually do something in that case, which is nice for that. But then we have some sub-packages for various interesting things. One is the control package. This is what we can use to do a safe kill or a safe change of control inside another thread. So one thread can say, hey, see this thread group? I don't want them to run anymore. Kill them. Send a termination signal to that in OSGi terms bundle and have that shut down reasonably. And then the system can reschedule other things at that time. And I think, people here have seen that, where you have a bundle that's poorly written, it does something suddenly that locks up the system or causes trouble for the system, and you have no good way of turning it down because thread kill is not safe. And it's not safe because finally clauses aren't run, which means resources aren't cleaned up properly. And the big difference of this mechanism is we ensure that that happens. Okay. Then the device package, this is a way of talking to devices in your system. You can attach it to event handlers if the system enables that. So raw memory is a way to map devices into your system and talk to them directly. So you can do a lot of the bus stuff without leaving Java, which is very convenient. Then you have happenings, which is how you attach external signals into the system, which you can use to implement device drivers. The enforcement is the other package that's interesting because here's I have mechanisms for limiting CPU use, memory use, number of threads, so that I can keep various bundles in bounds. And if they go out of bounds, I can take the appropriate action. For CPUs, drop the priority into the basement, so everybody else can run first. For memory, you get a normal out-of-memory error, even though the heap still has memory, but if you've used up your contingent, then you're dead, And then number of threads, it's easier. Just, you get an error at starting a thread, and it's, out of threads. So you get normal kind of Java responses to things in those two cases. Memory is something that provides a different way of doing memory reclamation. Basically, it's sort of stack-based. This was one of the reasons why we put this stuff out in other packages, because this is a pain to implement. And if you have a real-time garbage collector, you don't really need it. There's only very few use cases where you need a response time that's so high that might make sense. And finally, POSIX, you'd like a standard way to react to POSIX signals and also to send them. So it makes it easy to communicate with other processes in a system because you can provide that. And of course, it's all guarded by security managers, so you can say which bundles can and can't use these facilities. Okay. So conventional Java, is just a recap, is the base language. Real-time Java is kind of a refinement, a superset that gives you some additional capabilities that I just spoke about. Okay, what does it mean to put that together with OSGi? Well, you get the nice real-time response, resource management, and you can put it together with class loader-based isolation, lifecycle management module update. So you get a nice environment for mixed critical systems, particularly if you want to change the behavior as you go. I mean, you can imagine smart city applications where you have some facility that you use only under certain circumstances, and otherwise you don't need it. Well, you can download it, use it, and then when you're done with it, you can stop it, or at least stop and start it when it's necessary. So what are the challenges to a robust real-time system? Well, as I said, system lockup is a big point. So you want to make sure that you have some kind of resource enforcement. Otherwise, it doesn't work. And actually, this helps normal OSGi systems as well, because it makes it easier to manage foreign code. But the other thing is, for resource enforcement, you need to add some things to the deployment model. You need to talk about what are your limits for these various things. So you have to have some way of communicating with the system what the bundle expects, and actually be able to look at it and say, okay, I can accommodate this or not. Safe bundle termination is relatively easy to do on top of the RTSJ with these packages. Okay, so actually, we could add real-time capabilities to the RTSJ with no API changes. Because all these things that you would like to do, you can do based on properties. So by constructing the way the system works internally, by pre-compiling the bundle 0, by ensuring that these resources are actually monitored and deployed, you can have this capability just based on additional properties that you put on bundles and properties that you put on the entire system. So just, I guess that's pretty quick here. Just to recap, the real-time and embedded specification for Java gives you the facilities necessary for adding this support, both for resource enforcement and for real-time. And of course, if you combine it with OSGi, you get a pretty powerful system for mixed criticality and dynamic systems. So, questions? Yeah.
So, can you give some application examples? Can be smart city or other domains?
Where we'd use the real-time OSGi?
That's right.
Yeah. We're using this for data acquisition in vehicles. So our previous system had these facilities in it as well, and now we've ported them over to OSGi so that we can do this. So we are currently in the process of our next release with OSGi to bring these to a data acquisition system. And we have more than 25 million vehicles, almost 30 million now, in the field that have been using this for the last 10 years, the underlying facilities for the last 10 years. And it's provided a very robust system for our customers. So
it's acquisition, processing, and some actuation?
Yeah, so what we do is provide not just data collection, but a configurable data collection. So you can ask questions like, if this event happens, then collect these data points for this amount of time, or if I collect in this, and I can synthesize a new signal based on what's there, or I can even have a model of what I expect, and if I deviate from the model, only then send data. So I have these facilities inside the system to be able to provide a much more cost-effective and flexible system. We even have a company called Haas that provides notification, and they just use this platform to add the notification to the vehicles, and it was just almost no effort on their part to do that. So this ability to adapt your system to new requirements and do that for cars in the field is a very powerful notion. So we focus on embedded, so our use cases are embedded. I mean, we use the real-time Java in other areas as well. But for OSGi, this combination data collection vehicles is a very, very strong use case. And I guess putting such a framework in the 5G network is also a very interesting use case because, again, you can add things to the network as situations change and start and stop bundles and, even prioritize things and say, well, this system should run when there's an emergency going on. We push everything out of the way if we have to, or only have certain other things running at the same time. And if there's no emergency, you can just shut it down. It's okay. Yeah.
So, obviously, you would need a real-time VM underneath
Yes.
Such a framework. And then you would need a special framework which then on bundle loading manages all these things and communicates with the underlying JVM, or do you is there a kind of framework extension to Felix, or
we can do a framework extension to Felix. I mean, basically we don't write our own full OSGi implementation. We take one and modify it with the things that we need for that.
And you can do all these things with the standard mechanisms OSGi gives you to modify the framework, basically.
Yeah, and the important point there is the CPU management, because we can guarantee that there's always some CPU left over for the management to happen. And without that, you can lock up the system extremely easily. But with that, it's pretty robust.
Okay, so just for my sake, you just put a bunch of other headers in the manifest, and your extension jumps in when the bundle is loaded, and then reads them. And
so a little detail. For instance, if you have a bundle that says I only can use 5 megabytes of memory, then when we set up the bundle, we have a thread group, or actually a child of the thread group, where we hang that resource restriction onto it, and that enables it for all the thread groups and threads under that. Okay, and it's easy as that, and we do all our stuff that way with this special facility. And if it's not a real-time bundle, we create a separate thread group, a normal thread group, because in a normal thread group you can't use any of the APIs from the real-time. So you can use the facilities, but forbid anybody underneath it to use them with that simple mechanism. We also have security manager stuff for bundles that actually need real time. We can limit the maximum real time priority that's being used to, et cetera. So it's relatively simple to bring into the system. The details are in the real time VM underneath.
Okay.
Yeah, so.
That's nice. Do you already have plans for when the security manager goes away?
Actually, I've done some thoughts about that to use the modular system to be able to add a layer on top of it to provide security manager for the calls between packages, because that's where you need it, right? So if I had more time, I'd spend more time with the OpenGDK guys and say, hey, look, there's another way to do this so that you can pay the penalty when you need it, but not when you don't, and manage it a little better, and the whole bit. But
make it an optional part, basically.
Huh?
Make it an optional part to have the security.
Right. Because there's an amazing number of applications that think they don't need it. I don't know why, but okay. And of course, in the latest spec, we've really tightened up the use of the security manager, so that nobody can say, hey, the RTSJ doesn't use it, why should we implement it? Because they're the ones who should use it. Well, we don't. Yeah, so.
Okay.
Any other questions?
Yeah, you're right on time.
Oh, good. So there's a bunch of slides afterward that go a little more detail about real-time systems. If anybody's interested, take a look at those slides and, send enough a note if you want. But we've even looked at things like certification and how you'd go about doing that. So,
Yeah.
Thanks.
Okay.